Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, we are very happy to have Yucheng Zhang give a talk. He's a PhD candidate at UC Berkeley in Michael Jordan and Martin Wainwright's group. He has made actually a number of very impressive contributions to different topics in machine learning, optimization, as well as statistics. And he also not shy about coding and software implementations, you will see. And also, most recently, he has been working on learning neural networks. So that will be focus on his talk.
Yeah, thanks, Lin, very much for the introduction. Let me see if the microphone works. Okay, so.
Yeah, you have one on your shirt, it's fine.
Okay.
It's okay.
Great. Yeah, so it's my great pleasure to give a talk here at Microsoft Research Redmond. And in this talk, I will mainly talk about some provable algorithm for learning neural networks. And since this is an interval talk, supposed to be an interval talk, so I will also, I will first spend a little moment to introduce myself. So I'm a fifth-year PhD student at UC Berkeley, working with Michael Jordan and Martin Wainwright. And my general research interest is to develop machine learning algorithms for building artificial intelligence. This is a broad area, so my interest is also a little elastic. In my personal perspective, there are three key challenges in the machine learning research. The first one is how to represent AI in a rigorous mathematical form. So that is the modeling part. The second question is, given a concrete model, how to learn the parameters of the model using efficient machine learning algorithm. And this problem can be challenging if it is a very complicated model or the corresponding loss function is not convex. And the third question is, given a complex model, we need to use a huge amount of data to learn it. And this scale of data is usually not feasible in a single machine, but has to be stored and processed in a distributed system. So the question is how to perform efficient machine learning on a distributed system. My research tries to answer these three questions in different aspects. And before going into the main part of this talk about learning neural networks, I'd like to spend a few minutes to quickly go through my earlier work and their connections to the above challenges to probably give you a more concrete idea of my research background. Okay. Now, let's start from a specific family of algorithms that have been interested in. So it is called a divide and conquer algorithm. And these algorithms divide a large-scale problem into smaller subproblems and combine the solution to the subproblems into a single solution for the original problem. This computation scheme is very suitable for distributed computing. And indeed, we have proposed some efficient divide and conquer algorithms for learning parametric models. Such algorithms are computation efficient in the sense that every machine only has to solve a small-scale problem after divide and conquer. It is also communication efficient in the sense that the computation on the separate machines are mutually independent, and there's only one round of communication required at the end of the computation. We also theoretically guarantee that the algorithm has optimal performance in the sense that if the number of machines is not too large comparing to the overall number of samples, then the optimal statistical accuracy is guaranteed. And all of these theoretical statements were verified by a real data experiment. We also find that the idea of divide and conquer can be applied to learning non-parametric models. For kernel regression, for example, the classical way of learning it requires a running time of n cubed, where n is the overall number of samples in the data set. We have proposed a divide and conquer based more efficient algorithm whose running time has been reduced from n cubed to almost linear to n. And also, the optimal statistical accuracy is guaranteed. And this is a very first efficient algorithm for kernel regression, which guarantees the optimal rate. I'm also interested in classical convex optimization algorithms, as the convex models are widely used in practice. A key challenge in convex optimization is how to efficiently minimize a convex loss function given a very large condition number on the loss function. The state-of-the-art empirical risk minimization algorithms, such as SAG, SDC, or SVRG, may need to take 1 plus the condition number divided by the number of sample passes over the data set in order to achieve a high accuracy. we have proposed a more efficient algorithm called SPDC, which improves this iteration complexity from 1 plus kappa divided by n to 1 plus square root of kappa divided by n. So it could be order of magnitude faster for very large condition, for problem with very large condition number kappa. It appears that the efficiency of the distributed optimization algorithm also suffers from the high condition number problem. For example, the convergence rate of the popular distributed algorithms such as ADMM or LBFGS has convergence rate depending on the condition number, which further depends on the overall number of samples in the data set. So it means that if you want to process a very large data set, then the algorithm will converge slow. We have proposed a more efficient algorithm called DISCO, which converges strictly faster than these popular algorithms. And we can show theoretically that its convergence rate is independent of the sample size. So it is suitable for processing very large data set. And all of the theoretical statements for SPDC and DISCO were verified by real data experiment. When people try to solve complicated problems, they tend to build more complicated models, such as non-convex models. A very important family of non-convex models are neural networks. And this will be the focus of this talk. So I will point on the discussion on the provable algorithms for learning neural networks to the main part of this talk. Besides learning neural networks, I have also been working on some other problems which are non-convex, including crowdsourcing problem. So the goal of crowdsourcing is to label a data set with the help of internet users. But since these labels are noisy, we want to infer the true label as well as estimating the quality of users at the same time. This requires a non-convex model whose loss function may have many local minimums. For this problem, we have a proposed efficient algorithm based on the idea of spectral method and the idea of EM algorithm, which guarantees the optimal performance. So this is another very nice example that the non-convex problem can be solved by carefully designed algorithms. Some other questions that I have been asking are more theoretical. And one of them is, what is the fundamental trade-off between communication cost and statistical accuracy for all possible machine learning algorithms on a distributed system? And this is basically an area that is not fully explored. So there are some very fundamental basic open questions. One of these open questions is, if you want to estimate the parameter of a probability distribution, and you have a distributed data set, sample IID from this distribution, then the question is, what is the best possible statistical accuracy given a fixed communication budget? And our work has established this trade-off for some very fundamental problems, including estimating the mean for Gaussian estimation and estimating the coefficient for linear regression or probability regression. If we have shown that this trade-off is essentially tight, in the sense that they apply to all possible distributed algorithms, and they are realizable by practical algorithms. Another interesting set of problems is distributed linear algebra. For example, if you want to compute the rank of an n by n matrix, which is distributively stored, or the number of eigenvalue of this matrix that above a specific threshold. For this problem, we have proposed a more efficient algorithm which uses the idea of randomization, which only communicates n bits for this goal. We have also theoretically characterized the communication and accuracy trade-off for all possible algorithms for this kind of problem. And interesting enough, we find that this trade-off dramatically differs between the deterministic algorithms and randomized algorithms. So this is some connection between communication and accuracy. And another interesting interface is between the computation and accuracy. In statistical learning theory, we know that the optimal accuracy is usually characterized by the so-called min-max rate, the min-max error rate. For some important problems, we know that there are exponential time algorithms that achieve this min-max rate, but there's no known polynomial time algorithm achieving the same rate. We study an interesting problem called sparse linear regression, which is also widely used, and show that it is necessary to rethink the notion of statistical accuracy under certain computation constraint. More specifically, we show that there's an arbitrarily large gap between the performance of the best exponential time algorithm and all possible polynomial time algorithms. This shows that the min-max rate cannot be achieved by any polynomial time algorithm. And indeed, we have to redefine the notion of statistical optimality for the class of polynomial time algorithms. And we have shown similar gaps for improper learning as well. I'm also interested in building machine learning systems, and one example is Splash, which is a framework that I designed and implemented for parallelizing stochastic algorithms. So Splash is a general-purpose programming interface that allows users to develop stochastic algorithms such as stochastic gradient descent or Gibbs sampling without knowing any detail about distributed system. But on the other hand, it is also an execution engine that can automatically parallelize the algorithm that the user implement on a distributed system. We have a built Splash on top of Apache Spark, and it has integrated with the Spark ecosystem. So the existing Spark users can very easily use Splash. And we have verified by experiment, by large-scale optimization or machine learning problems, that Splash is able to achieve order of magnitude speed up over the official machine learning package of Spark. And this is partially because of the advantage of stochastic algorithms over the traditional batch algorithm for machine learning, and partially because of the efficient design of Splash. And this is an open source project which is available online. And through this URL, you can find some guideline for programming, installation, and some examples that you can try on your laptop or on any cluster. I also love to apply machine learning techniques to real-world problems. And one example is click modeling. The goal is to model users' behavior in web search and analyze users' feedback to the search engine to improve the search engine's ranking function and online advertising algorithms. This line of work was done when I was an intern at Microsoft Research Asia and eventually shipped into product to improve Bing's NDCG by more than 0.8%. I've also been working on some recommender system project, and the goal is to learn a non-parametric model to solve the data sparsity problem for online shopping recommendation. And this work has dramatically improved the quality of recommending long-tail items in online recommendation. So roughly, these are the works that have been done in the past. If you are interested in any one of them, you're more than welcome to come to talk to me after this presentation for more details. OK. Yeah, so it was an internship project at Google. So let's go back to the main topic of this talk about the Provable algorithm for learning neural networks. This is a joint work with my 2 advisors, as well as my colleague Jason Lee, who is now a postdoc at UC Berkeley. Right. In recent years, we have all witnessed the great success of neural networks in many applications of artificial intelligence, including vision, speech, NLP, reinforcement learning, and many others. Comparing with the classical linear models, we know that the neural network is able to encode nonlinear functions, which makes the model more powerful. Another benefit of using neural network is that it allows the researchers to incorporate their domain knowledge into the design of the architecture of the model. And it has been shown in practice that a specifically designed architecture can dramatically outperform the generic architecture, even for neural network. And successful examples, as we know, include convolution neural net, LSTM, and recurrent neural net. Despite the diversity in the model architecture, the algorithm for learning these model parameters are relatively uniform. People usually formalize the learning problem as an optimization problem by constructing a loss function and then run any optimization algorithm to minimize the loss function. So let's consider a simple neural network which contains only one neuron. It takes a feature vector x as input, and then take the linear transformation, then apply the sigmoid function to define the output. If you want to solve a regression problem, we can write the loss function as the empirical least square loss. Since the sigma is not a linear function, this loss function may not be convex. So it means that there could be multiple local minimums in the loss function. And if you run gradient descent to minimize this function, then there's no guarantee that the algorithm will converge to the global minimum. The problem of local minimums exists even if we only consider 2 points in one dimension. For example, if you choose the feature value pairs taking these 2 values and shape the landscape of the loss function here, you'll see there are 2 local minimums immediately. And the second local minimum is substantially higher than the first one. So if you run gradient descent initializing in this region, then it is likely that the algorithm will converge to the second minimum, which is obviously suboptimal. The classical way of solving the local minimum problem is to do multiple rounds of random initialization and then run gradient descent. So we can do this for multiple times and choose the best solution that achieves the smallest loss function value. This general approach can be combined with many heuristics. which improve the performance in practice. For example, we can use mini-batch training to improve the efficiency of gradient descent. We can use the momentum method to improve to get out of the bad local minimums, and we can use dropout to improve the robustness of the training procedure. It has been shown in practice that the proper combination of this general approach with the heuristics can achieve very decent performance on real-world problems. But does it mean that this approach is the correct way for solving all kinds of learning neural network problems? The answer is negative, because there is essentially some interesting problem, some interesting neural network that is difficult to learn using this gradient descent and random initialization approach. To see this, let's look at a concrete example called learning parity function, which is a famous and classical problem in learning theory. The problem setting is that we have a feature vector x and a label y. The feature vector is uniformly sampled from the vertices of a 50-dimensional hypercube, and the true label is defined as the product of a subset of coordinates of the feature vector. The number of coordinates involved is called the degree of the parity function, and is indicated by this letter p. The learner observed the feature vector as well as a corrupted version of the label. With probability 0.9, it observed the true label, and with probability 0.9, with probability 0.1, it observed a negative of the true label. The goal is to train a classifier using multiple instances in this form, such that given a new feature vector, it can predict the value of y, whether it is equal to -1 or equal to 1. So this image plots the true value of the parity function given two involving coordinates. If both coordinates are equal to -1 or equal to 1, then the true value is equal to +1. Otherwise, the true value is equal to -1. It's pretty easy to verify that this distribution of positive and negative samples cannot be separated by any linear classifier, but it can be separated by a two-layer neural net. So this is a classical example of showing the limitation of linear classifiers and the power of neural nets. We are not training a two-layer neural net for solving this problem. And because the loss function is not convex, we use multiple rounds of random initialization and backpropagation to train the neural network. And here's the result. If the degree of the parity function is equal to 2, then the algorithm successfully learns the parity function by using two hidden nodes in the only hidden layer, and achieve the optimal classification error of 0.1. But if the degree of the parity function is equal to 5, you can see that no matter how many hidden nodes it's using, the algorithm fails to learn the parity function, and its classification error is always around 0.5, which is the error.
So have you tried this problem using rectifier unit rather than sigmoid?
So I haven't tried both sigmoid and rectifier. Yeah, if I remember correctly, I haven't tried rectifier. And they have the similar behavior. So it means that on this more complicated and more nonlinear function, backpropagation doesn't really outperform random guessing. Now, this observation motivates us thinking about the following question. If you observe that a neural network fails on a particular task, then we want to know what is the true reason of the failure. There are two possible reasons. The first one is that the neural network architecture is not powerful enough, so that it cannot encode the function that we try to learn. And the second possibility is that the learning algorithm is not good enough, so that even though the good neural network exists, it cannot be learned by the algorithm. And in perspective optimization, the algorithm is trapped in bad local minimums. For this particular problem of learning parity function, we know that the two-layer neural net is able to encode the parity function. So it must be because of a bad learning algorithm. But for the more general and more complicated problem, it's really hard to distinguish these two reasons. So we don't really know what to improve if we observe a bad performance. So this motivates us to think about provable algorithms. If we know that the algorithm probably learns the model, then if we observe a bad performance, then we must modify the model to reduce the prediction error. Instead, if we observe a slow algorithm, then we must modify the learning algorithm to improve the running time. So in this way, the design of the model and the design of the algorithm has been clearly separated, which is a good tradition in machine learning research.
So when you didn't actually get the point with p equals 0.5, is it theoretical result that you cannot reach that, or is it empirical running that you try?
It's an empirical result.
But how do you know you apply all of the tricks?
So I'm sure that when you apply tricks, there's a pretty good chance that you can improve that. So one point is that this is just an empirical illustration for the motivation of the work. And you're absolutely correct that there could be other possibilities. Yeah. So more precisely, there are 3 questions that we want to answer for provable algorithms. First one is, under which assumptions we can show that a neural network is efficiently learnable in polynomial time. And second question is, if we weaken these assumptions a little bit, then can we show that there's no efficient algorithm possible under some classical assumptions? And third, we do want to know if this theoretical understanding can help us to design better algorithm that also works on real data. So I hope that I have motivated that this is an interesting question. So here's the outline of the talk. First, we'll first study a simpler problem called learning linear classifier with non-convex loss. And we'll find that the idea for solving this problem will be useful for solving the more complicated problem of learning neural networks. Then we'll proceed to the proper learning of neural networks and show some algorithm as long as there are theoretical guarantees. We'll also talk about improper learning, where the goal is to learn an arbitrary classifier, which is not necessarily a neural network, but we want its performance to be competitive with the best possible neural net. We're also going to show an algorithm and the corresponding theoretical result. OK. So let's start from learning linear classifiers. To formalize the problem, let's assume that we are given a training set of instances, and every instance takes this feature value pair form. The feature is a d-dimensional vector, and the value is either -1 or 1. So this is a simplified binary classification problem. The goal is to learn a vector w such that the following loss function is minimized. So this function h is an arbitrary function that measures the classification loss on a single instance. Typically, we like to choose h to be the step function, so this loss is exactly equal to the classification error. But unfortunately, we know that even approximately minimizing this function is NP hard. The hardness of this problem comes from the fact that the loss function is not continuous. So it is reasonable to use some continuous approximation to the step function and assume that h is L-Lipschitz continuous. But if L is very large, then the problem is still challenging, because it can be proved that minimizing this loss function in poly L time is still NP hard. It is a known result. So it motivates us to assume that L is a constant that doesn't grow with the sample size or the input dimension, d. So let's see some examples of loss function that satisfy this condition. We can consider a piecewise linear function which is equal to 0 if x is below a negative threshold and equal to 1 if x is above a positive threshold. It's a linear function in between. We could also certainly consider some smoother approximations, such as the sigmoid function. And for both functions, their Lipschitz continuity is characterized by this constant L. So given a loss function, what is the most straightforward way of minimizing this loss function? We have mentioned that a very natural choice is to first do random initialization and then run gradient descent. Right? For the simplicity of statement, let's assume that the minimizer of the loss function W star has a unit norm. And we also assume that the data is normalized, so that all of the feature vectors has a unit norm, or it is contained in a unit bill. The first step of the algorithm uniformly sample a random vector from the unit sphere of the d-dimensional space, because we know that the correct solution lies on the sphere of the unit, the surface of the unit sphere. And then we treat W0 as an initial point and run gradient descent or any optimization algorithm to improve the loss function value. Eventually, we'll get a vector W, which is also contained in a unit bill, and whose loss function value is at least as good as the initial point. We do this for multiple times and choose the best vector that achieves the smallest loss function value as the final output. This is a widely used approach. The first initialization step is very simple, and optimization step is very flexible. But in a theoretical perspective, it is problematic, because the loss function is not convex. And the second optimization step does not guarantee that it will converge to the global optimum W star unless the initial point W0 is very close to W star. But what is the probability that W0 is very close to W star? Since we are initializing a high-dimensional space, this probability is extremely small. And it's easy to verify that if you want to guarantee a high probability that a good initialization appears at least once in these iterations, then the number of iterations must scale as 1 over epsilon to d minus 1's power. So this is an exponential dependence on d, and too expensive unless d is very small. So the question we must answer is how to remove this exponential dependence on d. Surprisingly, there's a very simple solution to the problem. We only have to modify one place of the algorithm. That is, instead of uniformly sample from the unit sphere of the d-dimensional space, we sample from a larger sphere of radius r, where r is strictly greater than 1. And all the remaining part of the algorithm is not changed. With this simple algorithm, there is an interesting guarantee. If you choose the hyperparameter r following this formula, then the algorithm is guaranteed to be approximately optimal with high probability. And the iteration complexity depends on a polynomial function of n, where the power only depends on epsilon. So if epsilon is a constant, then this is a polynomial time algorithm in both n and d. If you examine closer into the theory, then it shows that the hyperparameter r is a trade-off between the efficiency and accuracy of the algorithm. If you choose a greater value of r, then you implicitly choose a greater value of epsilon. It means that the algorithm will be less accurate, but since the running time has inverse dependence on epsilon, it also means that the algorithm will run faster. So this is a very simple initialization scheme, which can have some theoretical guarantee. But it does have some limitations that we want to overcome. So 3 of the limitations are, first, the output of the algorithm will have a radius of r, and it's not necessarily contained in the unit bowl. But we know that the optimal solution is contained in the unit bowl. So it is not exactly a proper learning algorithm. It may cause some overfitting. And second, the constraint on W star and on all of the feature vectors are in terms of the L2 norm and cannot be generalized in LQ norms. But in practice, in many cases, we want to impose other norms like the L1 norm to impose sparsity. So this difficulty is because that in the proof of this theorem, we use the Johnson-Lindström lemma, but this lemma only preserves the Euclidean distance instead of the arbitrary LQ distance. And the third problem is that the iteration complexity is a polynomial function of n with a relatively large power. So,
I'm sorry. If we go back to this result, I mean, you're already rushing ahead to the next iteration. So here, I mean, you're assuming that the function is defined over the entire space, but the optimum is on the unit sphere.
Yes.
And somehow that, that assumption allows you to prove your theorem. So somehow the basis of attractions around W star become bigger when you go farther away. Where something is hiding here. I mean, you somehow, you're making some assumption. It cannot be just an arbitrary objective function. If I could choose any objective function, of course I can, make the points that are far away, have, some fractal structure, well, not fractal, but some very, very delicate structure of local minima that you will always get stuck. But somehow your assumptions are making the problem nicer. Can you shed some more light on what is the key here that makes that going farther away?
Okay. So one key assumption is that your objective function has to be continuous with a constant Lipschitz constant. Another key assumption is that the data should be IID. So the intuition behind this theorem is that if you consider some optimal solution W star, then this W star affects the loss function only by the inner product between W star and these features, right? So if you can preserve the inner product, then you can approximate the the loss function and even approximate the optimal solution. And now we know that W star is in a high-dimensional space. And now we construct a random subspace and just project W star onto this smaller dimension random subspace. Using the Johnson-Lindström lemma, you can show that after this projection, if you scale this vector by another factor of r, so r is a factor that is greater than 1, then the inner product will be preserved. There's indeed a dependence on the number of samples, because we know that as the number of samples increases, the dimension after the projection will increase logarithmically as a function of n. But this is only a logarithm dependence. So this factor r comes from the Johnson-Lindström lemma. When you're after you're doing the projection, you have to scale all of the vectors to preserve the distance and preserve the inner product. And why don't we have to construct this random space in the algorithm? It is because that you do 2 consecutive steps. The first step is to construct a random space, and then you draw from the unit sphere of that low-dimensional space. But combining both is equivalent of directly drawing from the original space, but with a greater radius. Yeah. So the projection step is hidden, but the fact of the projection is this greater radius.
There's no assumption about the convexity of the loss function.
There's no assumption on the convexity.
And you're guaranteeing that this algorithm will always converge to the optimum.
Actually, it doesn't. So there's no notion of convergence because the optimization step is arbitrary. So it's just a random initialization, and then you can, in the simplest case, you can directly output the initialization as your solution. But in the third step, you repeat it for multiple times, and there's a selection here. You use the loss function to choose the best one. So this step is also very important.
It's just the loss function that you're talking about, not the...
Yeah, so there's no convergence, because it could be just a random initialization and selecting the best solution, selecting the best sample. Okay, so we know that there has some limitations, and it can be solved by a slightly more complicated algorithm by constructing this initialization using a least square problem. For this more general algorithm, we can assume more generally that the feature vector has an LP norm that is bounded by 1, and all of the feature vectors has an LQ norm that is also bounded by 1, where P and Q satisfy this normal condition on the conjugate norms. The first step of the algorithm sample this k IID instances from the training set, and then sample a vector U uniformly from the k-dimensional hypercube. And then it solves a least square problem to compute a vector W0 in the original d-dimensional space. Then W0 is treated as an initial point. And then you can run any optimization procedure to improve it. And then we repeat this procedure for t times and choose the best one using the loss function, and then define the output. So for this modified algorithm, there is a better theoretical guarantee. If you choose k properly, the hyperparameter k properly, then the algorithm guarantees to be approximately optimal with high probability, and iteration complexity is exponential function on epsilon. And comparing this theoretical result with the previous one, you can see that there are 3 improvements. First, the algorithm always returns the vector in the unit bill, so it is a proper learning algorithm. And second, it applies to arbitrary LQ norms. And it has a better iteration complexity, because it has replaced the dependence on n by the dependence on a universal constant e. The proof of this theorem is even simpler. You first define a sample-based empirical loss function g, which only depends on your random samples. And then, using the classical learning theory, you can easily show that minimizing g will approximately minimize the original loss function L. On the other hand, it is easy to see that g of w for any vector w is uniquely determined by this vector of inner products. It's a k-dimensional vector. And using the norm constraint, it is also easy to verify that phi of w star is contained in the k-dimensional hypercube. So if you draw a vector uniformly from the k-dimensional hypercube, then no matter where w star is, u will be sufficiently close to u of phi of w star with probability on the order of epsilon to the kth power, because this is a k-dimensional space. Now, if you assume that u is sufficiently close to phi of w star, then we can solve this least square problem. This will give you a vector w0 such that phi of w0 is close to u, and we know that u is close to w star. So w0 is almost equivalent to w star in minimizing the loss function. And we get a good initialization with probability epsilon to the kth power. And we can repeat this for multiple times to guarantee the high probability bound. So the number of iteration is 1 over this quantity, and plugging the value of k into the expression, you'll see that iteration complexity exactly matches the theoretical claim. Okay, so these are algorithms for learning linear classifiers without any convexity assumption. Now let's proceed to the learning of neural networks. Before describing the algorithm, let's first define the function class that we want to learn. If the neural network has only 1 layer, then it is exactly a linear function, right? So it reduces to the problem that we have just studied. If the neural network has multiple layers, then for the m-layer neural nets, we recursively define it as a function mapping from the feature space to a real number. And a positive number indicates that it is a positive class, otherwise it is a negative class. And this function is a linear combination of several components. And every component depends on a lower level neural nets. So it's m-1 layer neural nets. The activation function is arbitrary, but we assume that it should be one Lipschitz continuous. It is a condition that is easy to satisfy. And the number of hidden nodes to construct the m layer is assumed to be finite, but otherwise it could be arbitrarily large. But we make this additional assumption that the L1 norm of all of the incoming weight of the combination coefficient is bounded by a constant b, and b is independent of the sample size or the input dimension. So this might be the strongest assumption of this work, but it makes sense in practice because the L1 norm constraint imposes some sparsely connected neural network. And we know in practice that the sparsely connected neural network is able to represent some meaningful functions that characterize the real data. For example, the convolution neural net is sparsely connected, and the sparsity of the connection could be independent of the scale of the image, only depending on the size of the slighting window, and independent of the cardinality of the training set. And we also know that imposing the L1 norm constraint in practice will improve the robustness of the neural network trained. So, given this function class, we also define the objective function as the empirical loss also characterized by this single instance loss function h. And f is the function that we want to learn. So it belongs to the neural network class. If the number of layers is equal to 1, then f is a linear function. So it reduces to the linear classifier learning problem. Otherwise, f is a more interesting nonlinear function. So we saw in the previous slide that the random initialization scheme can help to learn a linear classifier if the loss function is not convex. So a natural question is, can the same idea be applied for learning multi-layer neural networks? Right? And the answer is yes. And here I'm going to present a generalization of the second algorithm for learning neural networks, for learning linear classifiers for learning the multi-layer neural networks. The first step is still to sample the k instances from the training set. In the second step, we generate a random neural network to treat it as an initialization and do it in a recursive way. If the number of layers to be generated is equal to 1, then we do exactly as generating a linear function, right? Because this is a linear function. So we randomly sample a vector u from the k-dimensional hypercube and compute W0 by solving the least square problem and define and construct the linear function using W0. If the number of layers to be constructed is greater than 1, then we construct this m-layer neural nets recursively. Because this is a recursive program, we can first generate a sequence of lower-level neural net called G1 through GS, where S is also a hyperparameter of the algorithm, following the same program. And then we solve an alternative least square problem to compute W0. Then we construct this m-layer neural nets F0 using W0 and all of its m-1 layer neural nets. If you compare these two least square problems, you'll see that the only difference are in the blue terms. In the first case, the blue term is the feature vector. And in the second case, it is the output of the m-1 layer neural network. So it means that for constructing weights for the mth layer, we use the output of the lower level neural network combined with this activation function as the feature vector. And this is intuitive. So we can recursively construct the weight of the neural network from bottom to the top. And we treat this neural network as the initial network, run backpropagation or any optimization algorithm to improve it until we get another neural network f, which is also in the function class and whose loss function f value is at least as good as the original neural network. And repeat this procedure over t times and select the best neural network that achieves the smallest function value.
Yeah, so you do this algorithm mainly for the purpose of doing some proof later on. But in practice, it will be much slower than the stochastic gradient descent.
In practice, we find that running gradient descent for the optimization step is much better than just directly outputting the initialization. So theoretically, we don't need this optimization step. We're going to see that there are still some polynomial time guarantee. But in practice, indeed, optimization helps a lot. And it is an open problem how to understand the role played by optimization. Yeah.
I think this question is how fast or slow this all compared with just running the.
It's just computation-wise.
Computational-wise similar.
Computationally wise, comparing to what?
To just
stochastic gradient descent, mini batch, for example.
That would be just
mainstream method.
That would be just the third step, right?
So on one hand, if you only consider computation, then on this specific class of problems that stochastic gradient descent works, there's totally no reason to use another algorithm which is, even it is comparable to stochastic gradient in efficiency, but we already know that stochastic gradient descent works. But for some other problem, like, for example, we'll show later that for learning parity functions, then there's no trivial way to make stochastic gradient descent work. But we're going to show that this method, combining with some other technique that we're going to introduce later, will succeed easily in learning that complicated function. Yeah. So this is one algorithm, but not the eventual one. OK, so because the algorithm is a generalization for learning linear classifier, this theoretical result is also a generalization of what we have seen before. If you properly choose the hyperparameters k and s, then the algorithm is guaranteed to be approximately optimal with high probability. And the iteration complex is an exponential function of epsilon and m. So if m is equal to 1, then this theoretical result reduces to the theory for learning linear classifiers exactly. If m is greater than 1, then as long as the target optimality gap, the number of layers to fit, the L1 norm constraint, and the Lipschitz constant of the loss function are assumed to be constant, then this is a polynomial time algorithm in N and D. And importantly, I also like to emphasize that we haven't made any assumption on the data distribution. So this is a purely agnostic learning algorithm. And this will be important for the future improvement.
Mention a little, give some more intuition about this least-square problem that you're solving, which is kind of, because you first presented it for the linear classifier, and then you used it for, the neural network version. So if you go to the previous slide,
yeah, sure.
The step, basically the first step under 2, when you draw this uniform vector u from the hypercube, basically when you're solving this least square problem, you're completely ignoring the y prime, basically the labels.
Yeah, exactly. So this is a very good point. So all of this initialization is performed in an unsupervised manner. We don't use any information in y. We only explore the structure of the input space.
But can you give some intuition about this? Because if data is well separated, right? This blind assignment of labels u plus minus ones to these vectors x, I can't see how it's not like one of the random vectors u approximates the structure or anything, right? How, if the data is well separated and it's an easy learning problem, then what's going to happen here?
I'll try to explain.
Right.
So minimizing a non-convex function is very hard, no matter it is a low-dimensional problem or a high-dimensional problem. And the only difference is that in a low-dimensional problem, you can just randomly try and evaluate. But in a high-dimensional space, it is exponentially expensive to randomly try, right? And we don't know how to do optimization. So what we can do is to just randomly sampling. And so the purpose of solving this least square problem is that we assume that U represent a mapping on the optimal solution, and U is in a low-dimensional space. So solving this, the purpose of solving this least square problem is to decode the structure of the low-dimensional space and map it back to the original high-dimensional space. Okay, and we know that. So we know that if your solution is close to the optimal solution in the low-dimensional space, then after mapping back, they could be far apart, but their performance for minimizing the loss function is also similar. So the point here is that in the high-dimensional space, you cannot be close to the optimal solution, but you can be close to it in terms of performance, right? So you can do it by sampling, because the performance only depends on the structure of a low-dimensional space. Okay, and now here's the key part. So far we have an algorithm which has an exponential dependence on 1 over epsilon. This is good if epsilon is assumed to be a constant, but if you have a large number of samples, you want the error to be diminishing. So you want epsilon to decrease to 0 as a function of n, right? But in that way, it will be too expensive because of the exponential dependence. So a natural question is, how can we improve it to be a polynomial time algorithm given some reasonable assumptions? So we need additional assumption because it can be proved. It is already proved in the paper that it is impossible to improve the exponential dependence to polynomial in the worst case. It is NP-hard problem. But it is possible under some reasonable assumptions. So what assumptions that we need? So the inspiration of ours comes from the fact that learning a linear classifier with 0-1 loss is NP-hard. But this problem will become easy if we know that the data is linearly separable. And in this way, you can formalize the learning problem as a linear programming problem, which is known to be solvable in polynomial time. So we're asking if the same intuition holds for learning neural networks. If you know that the distribution of data is separable by some neural network, then does it mean that it is easier to learn a neural network that actually separates data? Before answering this question, let's first define the notion of separability. We say that a data set is gamma separable if there exists some unknown neural network called f star, such that for any instance in the training set, you have a y times f star of x is lower bounded by gamma. So gamma is the margin of classification. And the distribution is called gamma separable if any random sample satisfies this gamma separability almost surely. Now, with this notion of separability, we can show the following theoretical result. Assume that the number of layers, the separability margin, the L1 norm constraint, and the Lipschitz constant of the loss function are constant, then there is an algorithm such that on any gamma separable data set, it trains a neural network of f hat such that it correctly classifies every data point with a margin on the order of gamma in polynomial time. And furthermore, we can show that on any gamma separable distribution, it learns the linear classifier to train to achieve an epsilon generalization error using a polynomial number of samples and runs in polynomial time. So you can see here that both the sample complexity and the time complexity has polynomial dependence on 1 over epsilon. So we have improved the exponential dependence to a polynomial dependence by assuming this separability condition.
What's the dependence on gamma?
It's exponential. So we have to assume that the gamma is a constant. And we also have hardness results showing that it is impossible to improve it to polynomial, even if you assume the separability. But under these assumptions, it is also a worst-case hardness.
The statement that you made, is it for this algorithm or for any algorithm in general?
No, I'm going to present this specific algorithm called BoostNet
for
achieving that theoretical result. Yeah. So the algorithm is actually running AdaBoost to construct the M-layer neural nets. In the first, so it is iterative. And in the first step of any iteration, it uses the standard AdaBoost technique to weight the samples according to the existing classifier. And then it trains a n-1 layer neural network called G, which achieves a classification error which is at most gamma divided by 2b worse than the best possible neural network. And then in the third step, it combines this m-1 layer neural net into the stronger classifier to construct the m-layer neural net. And of course, finally, we may need to do some normalization to ensure that the neural net belongs to the function class we define. So I would like to share 3 insights why this algorithm works in achieving this theoretical result. The first insight is the equivalence between separability and weak learnability. So more precisely, it says that if the data is gamma separable, then for any reweighting on the data, there exists some neural network called G star, which achieves a classification error bounded by 1/2 minus gamma divided by b. And recall that 1/2 is the error of the random guessing classifier. So it means that G star is a non-trivial classifier whose classification error is bounded away from random guessing. Now please look at the second step of the algorithm. This trains a neural network G whose classification error is at most gamma divided by 2b worse than G star. So the classification error of G is upper bounded by 1/2 minus gamma divided by 2b. And this is still bounded away from 1/2, which is sufficient for AdaBoost. On the other hand, the optimality gap of G is assumed to be gamma divided by 2b, which is assumed to be a constant, because gamma and b are assumed to be constant. So we can use the agnostic learning algorithm we just developed in this talk to implement the second step. And this is a polynomial time algorithm in terms of n and d.
How does the alpha weighting play into the training of the net?
So the role played by alpha is that you first train a n-1 layer neural network and evaluate it. And if some samples are correctly classified by the first neural network, then the weight will decrease. Otherwise, the weight will increase. So you will focus on the hard samples. You always focus on the hard samples given the existing classifier. So that is the intuition of boosting to train incrementally a sequence of classifiers, and everyone just to focus on the hard example at the present stage.
I guess I'm asking what do you like focus on the hard example? How is that done with the neural net?
So you first have this function f, which is an m-layer neural net, right? And given this f, you go to the next iteration, and you assign alpha to be proportional to this. So you can see that, OK, I can see here. So there's a minus sign here. If f times yi is positive, it means that you have a correct classification, and the weight will be small. Otherwise, the weight will be large. So yeah, this is the specific way how it is implemented.
Figure into the actual loss function.
The actual loss function, you can consider the exponential loss. That is the standard way of analyzing AdaBoost. But here, we are interested in classification error. So because the exponential loss is an upper bound on the 0, 1 loss, you can transfer the convergence on the exponential loss to the convergence on the 0, 1 loss. And
is the traditional AdaBoost loss function embedded with the H?
Traditional? Sorry?
It says on the alpha weighted data. You take alpha and weight the data.
Yeah, I know, but OK, I see. So each of those terms. So are these weights like additive weights? What are those? Are they multiplicative with each of the loss terms?
Oh, so if you have alpha weighted data, then alpha is multiplied to every loss on the single instance. And all the algorithms that I presented before can be generalized easily to present weighted data. So that is not a problem. Yeah. And now if you have these V classifiers which can achieve non-trivial classification error, then the standard theory of AdaBoost guarantees that after order 1 over gamma square iterations, the classifier learned will correctly classify every data point with a margin on order of gamma. So this established the first claim of the theorem. And the second claim follows as a direct consequence of the first claim. Because if the first claim can be established with this constant margin, then you can show that the generalization error of the same classifier will be upper bounded by epsilon if the number of training instances scales as 1 over epsilon square. So the sample complexity has this polynomial dependence on 1 over epsilon. And since the running time also has a polynomial dependence on the sample complexity, so the running time also has a polynomial dependence on 1 over epsilon. Now, given these theoretical guarantees for the BoostNet algorithm, let's see how it performs in practice. And we revisit this problem of learning parity functions, where we know that backpropagation fails. So for learning a parity function of degree of 2, both algorithms learns the correct parity function and achieve the optimal classification error. But the BoostNet algorithm incrementally constructs its hidden nodes, and it constructs 5 of them until it achieves the optimal rate. So it's slightly less efficient than backpropagation. On the other hand, if the degree of the parity function is equal to 5, then we know that the backpropagation is roughly equivalent to random guessing. But BoostNet is able to learn the correct parity function by incrementally constructing less than 50 hidden nodes.
So in BoostNet, do you do gradient descent after the random?
Yeah, we do gradient descent. And if you don't do gradient descent, it's much, much slower than this. Yeah. OK.
Probably there are a few hyperparameters you have to tune.
No, we don't do any careful tuning. It's just
so gradient is in the number step 3 where you just go through a few iterations as long as it actually reduce the loss function.
Yeah. Yes. Yes.
So why does the parity function satisfy the assumption? You need gamma separability, right?
Actually, so there are 2 points. The first point is that it doesn't satisfy the gamma separability if there's noise, right? But because of the symmetry of the noise, it's roughly satisfied the same structure. This is the first point. And this is empirical result. So it just shows that the algorithm also works under the case where the assumption is not exactly satisfied. And the second point is that in the paper, we do have an extension of the algorithm that can work, in this case, with radical guarantee. So with some corrupted version of the separability, which is satisfied by the parity function. So it is in the paper, but not covered by the talk. OK, so we know that both algorithms learns the same architecture, the two-layer neural nets, but the second algorithm learns a better neural net. And in the perspective of optimization, it means that BoostNet is harder to be trapped in a bad local minimum. Because if you're trapped, then you add another node. So it is an incremental algorithm, and it's easier to get out of the bad local minimum. And that is the intuition, why the empirical result is better.
So why would I choose a BoostNet over like a boosting with just neural networks? You know,
yeah, exactly. That is a great question. So I think the intuition that is provided by the experiment is that you do want to choose boosting over neural networks. to construct a deeper neural network. You can even do this recursively to, like this is just the boosting one layer, but you can boost in many layers. But theoretically, the intuition that this work shows is that instead of using boosting alone, you also have to do very careful initialization. And in practice, you also know that initialization is important, right? So the initialization combined with boosting can achieve this polynomial rate, but any one of them alone cannot.
Have you tried experiments just with boosting on neural networks?
I do have a try using boosting, but less careful initialization. And it can still achieve something like that. So it shows that empirically, at least for this problem, it is boosting that is more important to the good performance. So finally, let's talk about some improper learning algorithms. As we have mentioned, the goal of improper learning is to learn some classifier that is not necessarily a neural network, but we want this generalization error to be compatible with the competitive with the best possible neural network. So it is at most epsilon worse than the best possible neural net. So this is the target. And how do we do this? The main idea is that we define another function class called f, and define f hat as the empirical risk minimizer within this class for the loss function. And we should define this function class satisfying the following three conditions. The first condition is that the empirical risk minimizer should be easy to compute. So it should be computable in polynomial time. Otherwise, there's no reason to choose another methodology. And second condition is that this function class should be powerful enough to contain the neural network. And third, it shouldn't be too large. Otherwise, it is too easy to overfit. So it is not too large in the sense that with a polynomial sample complexity, the generalization error of the empirical risk minimizer can be controlled by the best possible generalization error within this function class, plus epsilon. And combining this inequality with the second property, we can show that so it is actually easy to see that the best possible generalization within f is upper bounded by the best possible generalization within the function class of neural networks. So combining this inequalities, we have achieved the target of this. Now the only remaining problem is how to find a good function class that satisfies these three conditions. And our solution is to use the kernel method. We define a sequence of kernels. The zero-order kernel is defined as the inner product between the two inputs. And the piece-order kernel is defined as a function of the p-1 order kernel. So given the inner product, all of these kernels can be easily computed, given a finite p. So we choose p to be equal to the number of layers that we want to fit. And it can be verified that k of m is a valid kernel function. So it induces a reproducing kernel Hilbert space. If we treat these 5 functions as the basis function of the reproducing kernel Hilbert space, we can define a function class, which is a linear combination of these basis functions. So f is still in the reproducing kernel Hilbert space, but we make the constraint that the L2 norm of this combination coefficients are upper bounded by a constant that only depends on the number of layers to fit, and the L1 norm constraint on the neural net. So if you define a function class in this way, you can show that it contains the neural network class. On the other hand, you can also show that this function class is not too large, in the sense that the random Merkle complexity of the function class with n random samples is bounded by this same constant divided by square root of n. So this satisfied the third condition of the previous slide, and this satisfied the second condition of the previous slide. Now the remaining problem is how to compute empirical risk minimizer efficiently.
So that's great, but how did you arrive at this kernel?
Yeah.
How do you arrive at this kernel?
That's not always.
So there are some intuition indeed. There's a very seminal paper by Shai Schwartz, Ofer Dekel, and another author several years ago, and they are talking about learning linear classifier with non-convex loss. And they're using a kernel that is similar to this. And it is a very interesting observation that if you stack these kernels, then it will be strong enough to approximate the neural network. Because the neural network is just recursively defined as a stack of the linear combination.
Yeah, but you have this special form of recursion. That's not quite normal.
This one?
Yeah.
So the intuition behind this is that you can expand this as a sequence of, as a sum of polynomial functions. So the basis functions are actually polynomial functions. And you can show that the neural network class can have a polynomial expansion, and the coefficient for that expansion satisfies this constraint on the L2 norm.
So you don't use the Gaussian kernel?
I don't use the Gaussian kernel, and indeed the Gaussian kernel is not strong enough to cover the neural network. Yeah. Although, like the practical performance of Gaussian could also be good.
So it contains an M for any sigma?
No. So I'm going to talk about the condition on sigma. So there's a condition. So the only condition on sigma is that it should be smooth, but sufficiently smooth in some sense. But I'm going to show some examples of sigma that satisfy this condition, and they are very, very close approximation to the standard activation function that people use in practice.
So are you familiar with this Lawrence Saul also had this multiple, deep kernel method? Is it similar to this? Or?
So I may have read that paper, and I think there are some similar ideas using the stacked version of kernels to approximate the neural network. And it is known that, yeah, the kernel idea has connection to the neural network. And so one contribution here is this theoretical justification for that connection, and the more rigorous justification of why they're connected.
This special kind of recursive kernel to do all the proof down the road.
Yes, exactly.
And using Lawrence, the stack kernel, you won't be able to prove.
I guess not, but I'm not sure because I need to look more carefully into the paper. Yeah. Okay, so the efficient computation is also easy because it is a kernel method. And by using the representer theorem, we know that the empirical risk minimizer can be represented as a linear combination of kernel functions. So it suffices to learn this combination coefficient. And this can be written in the standard way into a convex optimization problem that can be solved efficiently. So,
sorry, why is it convex?
So this is a convex constraint.
Sure.
And H, where's H?
H is loss.
Oh, so H is a convex function. So H is the final penalty on the output of the neural net. So you can choose, for example, the hinge loss. And if you can minimize the hinge loss, you can get an upper bound on 0, 1 loss.
How many times do you need to recurse when you define the kernel?
So it depends on how deep the neural net we want to. Yeah, it is the same as the depth that you want to fit. Yeah.
Yeah, I have seen quite a number of papers using kernel for neural net. The intuition is that if you use this Gaussian kernel, you effectively can get infinite size of the hidden units. But using this kind of recursive kernel, do you have that property?
Infinite number of yes. So. Oh, so actually this can approximate any neural network in the class of neural networks that I defined in an earlier slide. So if you recall that definition, the number of nodes in that function class can be arbitrarily large. So it could even be infinite in the limit. And the problem of the Gaussian kernel actually is that the Gaussian kernel can fit any function that is sufficiently smooth, but that condition on the smoothness is very, very strong if the dimension is high. But the neural network class contains the function that doesn't satisfy the smoothness condition. Yeah.
Just trying to understand the relationship between the number of hidden nodes and the level of recursion. So you mentioned the level of recursion should be same as the depth.
Yeah.
But how does the number of hidden units and layers?
It is not related, but it is related to the L1 norm constraint, B, right? Because B appears in the algorithm. Yeah. So it turns out, so it is a well-known fact that if you make a constraint in the L1 norm constraint, then the complexity of your function class could be independent of the number of nodes. Yeah, so the L1 norm constraint is also a strong constraint, which can control your complexity. So putting all the pieces together, the theoretical guarantees that if you assume M and B are constant, and sigma is smooth enough, I'm going to show what smooth enough means, then the classifier trained can be computed in polynomial time, and the corresponding sample complexity for achieving an epsilon generalization error is also polynomial. You can compare this result with the theoretical guarantee for BoostNet. And we're going to see that it doesn't need any separability condition on the data distribution. So it means that by moving from proper learning to improper learning, you're considering a wider class of algorithms, and now you can achieve similar learnability result with a weaker assumption on the distribution. The only additional assumption is the smoothness condition on sigma, which I'm going to show two examples. So you can consider the ERF function that satisfies that constraint, and it's a very close approximation to the standard sigmoid function. You can also consider a smoother version of the hinge loss, which is a smoother approximation to the standard ReLU function. So for both the standard sigmoid and standard ReLU function, you can find some very close approximations. So this approximation is one of them, but can be even closer, as long as the smoothness constant is a universal constant. So for both standard functions, you can find some approximation that is close and satisfy the constraint of the series. And finally, we also have some simple experiment to test the algorithm on the MNIST dataset. Because the original MNIST data recognition task is relatively easy, we also compare with some variations of MNIST, including randomly rotating the digit by some random angle, or adding the noisy background into the image, or combining the rotation and the noisy background. So roughly speaking, the experiment says that the kernel method outperforms logistic regression and the backpropagation trained two-layer neural networks. But it is not, so it is comparable with the convolution neural net on basic and rotation dataset, but not as good on the other two datasets. This is also expected because the kernel methods, we just design a generic kernel instead of using any property of the recognition problem. But the convolution neural net indeed uses the domain knowledge. Another observation is that if you increase the hyperparameter m, it means that the model will be able to fit deeper neural networks, and actual performance also gets better in all cases. And this is also intuitive because you can expect that the performance of a deeper neural network can be slightly better on the MNIST dataset. Okay. So as a summary of this talk, we have studied the Provable algorithm to learn constant depth neural networks in polynomial time. The take-home message is that for improper learning, there are two conditions needed. The first one is that the incoming weights of all the neurons has an L1 norm bound, which is a constant. And the second condition is the separability condition on the data distribution. And under these conditions, you can show that the neural network can be learned in polynomial time. And for improper learning, we also have two conditions. The first one is still the L1 norm constraint on the neural network. And the second one is the activation function is sufficiently smooth. So in summary, we know that learning neural network is a challenging problem. It is NP hard in the worst case, but it could be easy if you add reasonable assumptions and use novel and principal algorithms. You can get theoretical guarantees. Okay. So understanding deep learning is a very challenging field, and there are certainly many open problems. And this work is only an early step in exploring, searching for the algorithm that are both understandable in theory and also useful in practice. And there are certainly many open problems, and we'll list the three of them. So the first open problem is that we know that in our algorithm, some quantities are assumed to be constant. And this is because that the running time of the algorithm has exponential dependence on these quantities. But on the other hand, we also know that some exponential dependence can be improved to polynomial dependence if we consider some additional constraint on the data distribution. Right? So it is very promising to consider some further properties of the real data distribution to further reduce the complexity of the algorithm to make it fully polynomial. And the second point is that it is a little weird to observe that a theoretical guarantee still holds even if your optimization algorithm does nothing. So it's just the output initialization. So it's very interesting to understand the role played by the optimization algorithm. And if you can have that understanding, it will definitely help the designing of the algorithm, because we know that in practice, the optimization step helps a lot. And third point is that, so the essential difference, as we have noticed, the essential difference between BoostNet and the traditional backpropagation is that BoostNet incrementally constructs a neural network, while the backpropagation trains a fixed architecture. But although BoostNet only constructs the top layer, I believe that using some novel technique, it is possible to design a better algorithm that incrementally constructs the whole neural network from bottom to the top. And every incremental step is very simple, very principled, and analyzable. And the combination of a large number of this incremental step will be sufficient to construct a very complicated neural network. And if this can be done, then a very deep and complicated neural network can be learned in a principled way and with theoretical guarantee. So this is a more ambitious goal. Besides learning neural networks, another field that I'm excited to work on is deep reinforcement learning, so I've also covered some points. So deep reinforcement learning is a branch of deep learning, and all the principal method that works for classical learning of neural networks can also be applied to deep reinforcement learning. So the effort that is done for the previous problem will not be wasted for deep reinforcement learning. On the other hand, the primary goal of my research is to explore the algorithm for building artificial intelligence, and I believe that a strong AI must interact with the environment and to take actions on the environment and to collect the reward from the environment. And reinforcement learning is exactly a methodology for doing that. So there are some unique challenges in reinforcement learning that some key innovations can be made. So one of them is that the current methodology of reinforcement learning uses neural network to approximate the Q function in the DeepMind work, and use that Q function approximation to make decisions. But the model itself cannot remember anything. On the other hand, in order to interact with a more complex environment, it is essential to maintain a memory that can collect the knowledge and experiences from the past experience to improve the performance. So it appears that a long-term memory mechanism is very interesting to incorporate and could be useful in practice. This memory could not only be about how to solve a specific problem, but also about how to interact with human beings, with many different human beings. So in other words, if you can personalize the reinforcement learning model, then they will find application in many interesting fields, including playing games with multiple players instead of just a video game with one player. The other applications may include interactive search or personalized recommendation, or even some business applications like decision-making, sales, or negotiation. On the system level, I think it's also interesting to build some interactive system that can interact with the internet users to actively collect data from the users and serve the user simultaneously with the model that is trained on this data. So roughly, these are a subset of interesting works that I think worth doing in the future. And more than happy to talk to any one of you about the details of that. So just to wrap up, we have a talk about some probable algorithms for learning neural networks and some past work of mine and some future works. So I'm looking forward to any further meeting with the people in MSR. Thank you very much.
What extent the method that you talked earlier on and the theoretical result can be generalized from binary classification to multiple classes? Or is it something that
so for both the improper learning and proper learning, there are binary classification algorithms. For improper learning, we do the MNIST dataset on 10 classes. And the way that we do it is just to train 10 one versus all classifiers. It is not bad according to the performance. So I believe that the proper learning can also be generalized to that. On the other hand, if you... It's not efficient as doing a native multi-class classifier. So it's a very interesting question. And I believe that you can define some notion of separability, at least with margin for multi-class classification. And you know that there are plenty of work on multi-class boosting. Right, so I think the idea can be transferred, but might be future work.
So I have a question about this gamma separability concept that you explained. So is this in your work that this is first proposed, or is it something that exists in the literature? I'm just curious to know.
Well, as far as I'm concerned, I don't know the other work because there are very limited work in the theoretical analysis on neural networks. But the separability condition is indeed a standard thing for learning linear classifiers. And we know that there's a connection between linear classifier and neural network if you consider non-convex function. So I think conceptually you can find some related work. But specific for neural network, I don't know any other paper that uses similar assumption.
My question was that then, basically, given a data set, based on like there are these theorems in machine learning, and I don't know the exact theorems very well, but there are theorems that say that basically, a neural network can approximate any function. And so, isn't it true that for a given data set, there will always be some neural network that will be able to achieve gamma separability?
So yeah, so first, it is not exactly true because it is possible that with the same feature, the label could be different because your data set could be noisy, right? If that happens, then no classifier can achieve perfect performance. On the other hand, so even though there are some results saying that a neural network can approximate any function, but that is under some smoothness condition. And if you look at a high-dimensional problem, then smoothness becomes a very serious problem because in the high dimension, there's a very interesting result in geometric functional analysis saying that if your function is sufficiently smooth, then it's almost a constant. So if you impose very strong smoothness conditions, then you cannot learn anything interesting. So the problem now lies on how can you weaken this smoothness conditions, and that is the power of neural network, I think.
A somewhat practical question. So I think the method you showed, you tested on, I think it was a 2-layer neural network, so it's very shallow. And it was a great result. You showed that by more intelligent optimization or more intelligent initialization, you could learn more complex classes of classifiers that backpropagation can't. That's great. In practice, when we meet that problem now, so this is a practical question, we tend to add more layers, and then that gives us more learnability property. I wonder if you could sort of comment on, what amount of depth might be required for that problem with standard backpropagation and random initialization. I'm trying to get a sense for how much compression might that have saved. Is it saving 1 layer or 10 layers? Do you have any? Can you speculate, or do you have any results?
Yeah, so that question is, so you're asking, so I think this can be understood in 2 aspects. The first one is, as you get a more and more layer, you get a stronger power of representation, right? So that might be one reason why they achieve better performance. Another perspective is that when the neural network gets deeper, it is even easier to train because you have more parameters and there are more local minimums. And actually, even if you go to one of the local minima, it is good enough. But if your neural network is shallow and small, most of the local minima is not good enough.
Personally, I think the second one is probably more important, but I think both are true.
Yeah. I cannot answer both questions explicitly. For the first question, it is basically a orthogonal question to this line of work because we don't care the representation power. We just assume that if the representation power is strong enough to classify your data, then we can learn this representation. But we cannot characterize what kind of distribution can be separated by a 10-layer neural net. And the second one is, if you want to answer the second question, I need to understand how optimization behaves in the landscape of the loss function of a 10-layer neural net, or at least a deep neural net. So this is a challenging problem, and still we cannot answer that. And the partial answer is, if you look at the boosting mechanism here, then the boosting is a special case of a greedy method because boosting can be understood as a greedy method, right? And we see that using greedy method can improve the complexity of the algorithm from exponential to polynomial in some sense. And what I believe is that the reason that a deeper neural network is easier to train is because it is a better architecture for the greedy method to work. Because gradient descent is also a greedy method. It's just a search over your neighborhood to try to find the best direction to descend, right? So I think there are some very strong connection between the greedy nature of gradient descent and the depth of the neural network or the architecture of the neural network. And it's a very interesting open problem to formalize them either by some new theoretical analysis on the gradient descent or by some new modeling technique such that you can build a new model that is almost as powerful as the traditional way of building a neural network. And for that new model, there's guarantee that it can be constructed incrementally in a principled way, like in the third point suggests. Yeah, so I only have some future visions, but there's no explicit answer on the question.
Okay, let's thank you again.